So this could be the most important technique to understand in chemistry and maybe even biology. This allows you to test for hundreds of different, thousands of different, basically endless compounds and even organisms, viruses, particles. It does all the work for you because you put it into a machine and it just measures out the values, the concentrations, and you're done. So no need for titration that takes you an hour. You can do thousands of measurements. Well, the machine can do it for you with a fraction of a drop. So we could use just like a little tiny, like 10 microliters, maybe it drops around 40 microliters using a pipette like this, and put it into a machine and it'll go down a tube. It'll react with various chemicals. So you might have an antibody that's got a reactant attached to it that'll bind to a specific virus, and it'll react with it. The intensity will give you the actual concentration. So how does the spectrophotometer look like? Well, first of all, I'll just go to what the finished product is. The finished product is you grab known concentrations and draw a straight line there, and then your unknown concentration can just be lined up here. So what are these things? These things are absorbances. And so if we go to what a spectrophotometer is, it's basically just a machine that emits light, and light will be absorbed, and it doesn't have, this one's light, but it can be all sorts of different things. Later on you'll learn there'll be other types of things that you can project into a substance and detect on the other side. So this one here, you just project light into a sample and the sample will absorb light. Now, how do you know what is the ideal absorbance for the sample? You use something here called a color wheel. So generally, if the substance is blue, for instance, which is what we're doing, blue food coloring, usually the orange wavelengths are around 600, which is what we're going to use, will absorb into this much better. And so we're going to use absorbance here. You could also use transmittance. Just a note of interest too, if you have a more expensive machine, you can actually get a graph like this that shows you the absorbances over a range of concentrations. You can see the blue does absorb well at 600. And for this one in particular, you can also see that the straight line, the chemical behaves in unusual ways at different concentrations. So this is from the research. You can see that the straight line isn't actually that straight of a line for this particular compound. So the first thing we're going to do, just to keep it simple and doable for you, I'm just going to make 5 standards. I'm going to do it 3 times, which you don't need to do. Once is enough, but I just want to have some sort of idea of error. So I'm going to measure it out 3 times. Now measuring is where all the errors are. So I did the measuring bit for it. And so we're just going to do 1 drop to 5 drops, and the unknown, which I'll just jump to now. So how do you make up the unknown? I'm going to put it in 15 mils. So 2 drops in 15 mils, so that'll work out to 1.3 drops per 10 mils. So you can add 10 mils of water each time. So to make up the standard, this may or may not be new to you. So you need to measure out using a volumetric pipette. So you need to get it to the meniscus like that, and then you need to deliver it. EX means you need to deliver it, not expel the last little bit of liquid. So I'll just put up a diagram here up here right now just to show you which one it is and which one you're meant to do. So for this one, I know it's to deliver, and so I got to hold it at 45 degrees for a couple of seconds, and that's the amount of liquid. I know I was being super sloppy and spilling stuff everywhere. There's evidence of it in standard 4.3. I'll just show a picture of it here, and you'll see in the data that one shows up. So most importantly, how to operate the machine is when you turn it on, you need to calibrate it. So to calibrate it, you'll put some water in there, and you'll make sure that it is put in through the clear side. So you can see the clear side, not the opaque side. And then you just close it and press OK. And then it'll know that that's 100% transmittance. Okay, so now you can fill it up. Usually fill up the cuvette to about 3/4. I think you can get away with a half. And so what I'm going to do now is each time you fill it up, go from low to high concentration to limit the amount of contamination with leftover drops and whatnot. Make sure that each time you fill the cuvette, you can see I do it every single time. You wipe all sides of it so it's nice and dry, so no liquid gets into the machine and destroys it. So that's probably the most important thing because these are expensive. So put it into the machine nice when everything's nice and dry each time, and close the lid, and then you take down the readings. So I'll just speed that up. You can see that I've got all those different types of readings there, and then we can process the results. Okay, so just going to the table there, you can see that quite clearly that did come up as quite different from the other 2 results. You really should get pretty much close to perfection. So the fact that I've got these absolute uncertainties of the mean, that's how you do it. It's just basically the lowest minus the highest, the range divided by 2. You can see I've got from the error bars over here, I've really got quite a large error bar on here because I was being sloppy on purpose. This line actually makes sense if I did actually compare it to published results. So I'm not actually sure until I do more analysis of it. So basically I got a reading of 1.97. So the equation of the lines here, I rearrange it for x, so I can just sub in the 1.957 as you can see up here. So that gives me a reading of basically 1.1 drops, which I was meant to get 1.3 recurring. So not very good on the accuracy there. So if I do a percent error here, so the difference between the two divided by the expected times 100. So I've got a 15% error, which is, you know, for high school chemistry, under 20% error is okay, but I was purposely sloppy and I probably could do better than that. There may actually be some errors with the actual way the chemical behaves at different concentrations as well, so that could be further analysed.